So this last thing that we're going to look at is whether, it's basically a vocabulary word, whether a series converges absolutely or conditionally. So that's the question they would ask. Does this series converge absolutely or converge conditionally? So if you do the absolute value of the series, if that converges, then you don't need to do any other work. The whole thing converges, and it converges absolutely is what we call it. So you do the absolute value of it, test that one. If that converges, then you're good. It converges absolutely. Now, if that one diverges, but the regular series converges, then we say it converges conditionally. Okay, so you always test the absolute value first, see what that does, then test the actual series if you need to. There is actually a third option that I didn't put on there, but I made example one do that. Well, I shouldn't have said that. Oops, pretend I didn't say that. Which is that instead of converging absolutely or converging conditionally, instead of converging, it can just diverge. Like that's the third option there. So what test would you think about using for this first one? And I realize it's alternating, but maybe sort of ignore that part. I would not do a ratio test. There's an easier one. You want to go for the easier thing. I would do the nth term test. If you do limit as n goes to infinity of this thing, the numerator is a factorial, the denominator is an exponential, but a factorial grows faster than an exponential. And so where does this limit go? Infinity. And so we can just go ahead and say diverges by nth term test. So it doesn't converge absolutely or conditionally. It doesn't converge at all. It diverges by nth term test. Okay, so that's like the third option. That's the only one I put on here that does that. So for number 2, we're going to look at the absolute value of the series. When you start to do these, you're starting to talk about different series. You have the absolute value one, and then you have the original one. And so you have to be careful to be clear which one you're talking about. And so if we absolute value this, it basically just gets rid of the alternating part of it, and you have 1 over square root of n. So we're going to talk about that and see if it converges or doesn't. So what do you think about that one? That is correct. Diverges because, and what's the reason why? P series with P equal to 1/2, which is smaller than 1. Okay, so let's stop there and assess what we did so far. We found the absolute value diverges. So we're right here. Absolute value diverges. But the original series could converge, and then we would, go, our big conclusion would be that it's conditionally convergent, okay? So now we're going to look at this series itself. We did the absolute value. Now we're going to look at this one. What test would you use for this one? Yeah, alternating series test, because it's an alternating series. Most of these are going to be alternating series. All right, so the first step, it's a 2-step test. Limit as n goes to infinity for this needs to equal 0. So does it equal 0? Yes. Most of the time, once you've decided to do an alternating series test, it's going to work. You just have to write all the things out to prove it. What's the second step for that? Keeps getting smaller. So I'm going to say 1 over square root of what? N plus 1 is smaller than 1 over square root of n. And again, I always just write out, basically it's like wishful thinking. I just write out what I want it to be so that I can see it. And then I decide if that's true. And is that true? Yes, the bigger the denominator, the smaller the fraction. So this is true for n1 onwards. So we would say converges by alternating series test. So again, let's stop and assess where we are. The absolute value diverged, but the series itself converged. So what's the big conclusion? Conditionally. Converges conditionally. Oh, let's try another one. This is -1 to the power all of that, which is good because it's just -1 to all of that stuff. So the first thing that we're going to look at is the absolute value. And you always do that first, because if that one just works, then you're done. You don't have to test the series itself. So you always want to test that first because you can save yourself some work. So the absolute value would just be 1/3 to the n. And I would actually rewrite that a little differently so that you can kind of see what's going on better. Can you think of another way I can write 1/3 to the n? Because we can make it look like one of our familiar series. Just kind of meddle with that algebraically a little bit. Yeah, 1/3 to the n. And you can even put a 1 out front if you want to. You said 1, so I'm going to put that there. So when you look at it that way, that helps you to kind of see the pattern a little bit better. So what type of series is this? Geometric, converges, or diverges? Converges. So we would say converges because geometric with absolute value of r equals 1/3, which is less than 1. So then let's stop and assess where we're at. We did the absolute value and we found that it converges. So we actually don't have to do any more work. What's our big conclusion? Converges absolutely. So again, always do the absolute value first because that'll save you some work. Let me just do one or the other of these because that's really all there is to this lesson. Let's just do 4 and I'll write up the answer for 5 and post it. All right, so let's do the absolute value first. So that's going to just get rid of the alternating part of it. It'll be 1/ln n plus 1. Unfortunately, that's not geometric and it's not a p-series. And it's not telescoping and it's not alternating anymore because we did an absolute value of it. So you need to figure out something else. I would do a comparison. I think if you can compare to something similar, then that's the best way to go. So we're going to compare it to 1/n. And again, the whole point of doing a comparison is you're comparing it to something that's a whole lot easier. Can I call this an easy one? I know none of this is easy because it's AP calculus, but can I call this an easier one? What do we know about this one? Diverges because why? P-series with p equals 1, which is less than or equal to 1. So here's the goal. We want to say, because this one diverges, this one does too. I like limit comparison. We were just having this conversation, but if you try and do a limit, just as a heads up, it won't come out to a finite positive number. So we're going to have to do a direct comparison. Now, if this one diverges and I want to say this one does too, that means this has to be the smaller one. If the smaller one diverges, then the bigger one does as well. So again, I always write it out the way that I want it to be true and then kind of see if that makes sense. I want this one to be smaller than this one. So is that a true statement? Yes, because a polynomial, I know it's just n, that's linear, but it's still a polynomial, is going to grow faster than a logarithmic. So the bigger denominator is the smaller fraction. So this is true for n bigger than 1. And so our conclusion is that this one, the absolute value one, diverges by direct comparison. And you have to be extra careful which series you're talking about when you do a comparison, because now there's actually 3 of them. You have the original series, you have the absolute value, and then you have the one you compared to. So you've got to be really careful which one you're speaking about. So that's why I rewrote this. Okay, let's stop and assess where we're at, because I realize it's a lot. We found that the absolute value diverges. So where are we as far as like being able to conclude something over here? We found the absolute value diverges. So like, what do we need to do now? Yeah, see if the actuals is, so we know it's not absolutely, but we can check if the series itself converges and see what goes on there. So what test would you do for this series itself? I'm gonna like bring this down here. AST, all right, so we're gonna do limit n goes to infinity of this, which does go to 0. The denominator keeps getting bigger and bigger, so that's going to go to 0. And then the second step of it is that you need to show the terms keep getting smaller and smaller. So I'm going to plug in n plus 1. So you'd have n plus 1 plus 1. That'd be n plus 2. Is smaller than the series itself. And so is that a true statement? Yes, this one's bigger, like bigger denominator, so it's the smaller fraction. So we can say converges by alternating series test. So what's the big conclusion to the whole problem? Converges condition. So do you see how it's not a new test? Like we didn't learn a new test or anything. It's just almost like a piece of vocabulary.